Thank you very much for spending some time with us today. My name is Monicelli and I'm a sales technician at the International Sales Department of WEG Automation. And I'd like to introduce today's presenter, Rafael Chirakashi de Souza. Rafael is one of our sales engineers with more than 10 years of experience with WEG Automation products in the Brazilian and in the international market. However, before we start, I have some information to share with you about this webinar. To make sure the sound quality is good, all microphones are going to be muted. If you have any question or clarification about Rafael's talk, we'd love to hear from you. So feel free to type it in the questions and answer chat. We have our sales team in the background prepared to answer your questions. If by any chance you miss some important points, don't worry. A recorded version of this webinar will be available, meaning you can watch it again later or send to a colleague. To do so, just go to WEG's LinkedIn page and click on Events. There you will find this webinar, the past webinars, and future ones from all the WEG divisions. Without further delay, I would like to welcome those of you just joining us and pass over to Rafael, today's presenter. Enjoy it.
Okay, good. So hello everyone, welcome to this webinar. Monicelli, thank you very much for the introduction. It's a very great pleasure to get you guys on board with us today, right? So as Monicelli mentioned, today the talk will be about the motor starters, all right? So we're gonna talk about the methods we have available to start induction motors. So guys, when I got assigned to this task, there was something that was in the back of my mind. How can I make an easy way or an easy presentation to you so you guys understand the fundamentals and the basics of the motor starters? Then I managed a way to put this into a presentation. So that's what we have today. Pretty much for the scientists and for the experts. This might sound a little bit simplistic or basic, but again, the intent here today is to get you guys to know the fundamentals or the basics on the motor starters and why to choose one or another option, okay? So let me present myself again quickly, just quickly. So my name is Rafael. I've been working for WEG for 13 years now. It looks like it was yesterday that I joined the company, but yeah, it's been 13 years. Some of these years here in Brazil and a few other years in Australia, okay? So that's why you're gonna get this different accent on my English. So today my role is a sales engineer and specifically for the low voltage drives and controls. And yeah, that's pretty much who I am, okay? So before we start with the technical points, let me jump to the agenda for today's talk. And I'm gonna get also the laser pointer. Cool. So guys, this is the agenda for today. So we're gonna start with the motor starting characteristics, right? So in this chapter, or let's say in this module, we're gonna talk pretty much about the current behavior and also the torque behavior of the induction motors when we are starting a motor. Then we're gonna jump to the GOL starter, which is a short for direct online. Past that, we're gonna get through the star delta starter, and then we're gonna move over to the soft starter, and then we're gonna finish it up with the comparison between those starters we talked about, right? So because my time here is, I just have 1 hour to talk to you guys. I didn't manage to get the VFTs on it, so that's the reason why you will see only these 3 starting methods here in the presentation today. Okay, so let's get it started with the motor starting characteristics. Again, this might sound a little bit simplistic, but it's the fundamental of the induction motor. So we need to understand that to jump into the methods, right? So, okay, I'm gonna get a shot in here for you guys, a graph, and that's the graph of the current versus the speed of a motor, right? And in this graph, we are considering the motor fed by a power supply which has a fixed voltage and also a fixed frequency on it, right? So what we can see in the graph, it's pretty much how the induction motor behaves to accelerate, right, up to speed. So in this point here, we have the rated speed. So what you can see, the rated current is just in there. And then to get to this speed, we have to pass through a region where your current will go up by a significant amount. So if you watch out in the graph, this is the level for the rated current. Well, when it's starting, this motor can get to very high current level, right? Okay, so we know now how is the behavior of these of the induction motors when starting, but where can I find this information, or where can I find this maximum starting current that I have in this graph, right? Cool. You guys can find this information on the motor data sheet, right? So in the motor data sheet, we have a parameter which is called LRC, which is the short for locked rotor current, right? So the locked rotor current is usually shown as a PU, which is per unit. That's an engineering way to say like a percentage, right? So in this case, he's 6.6, which means this specific motor from this data sheet, when starting, the maximum starting current will be 6.6 times what your rated current is, right? So for this specific one, your rated current is 525 amps, then you have 6.6 times, and then you also have here the locked rotor amps, which is 3,470 amps, right? Cool. So we know how the current behaves, we know where to find information. So what is important from this, right? So what is important that we need to know when we're starting an induction motor with the rated voltage and frequency, right? High current level is expected while you're accelerating that motor to the rated speed, right? So that's what you need to gather from this fundamental of the induction motors. Good. So we are done with the current. So let's move over to the torque. And now I'll bring a few more graphs as well, because that's the best way to learn about it. All right. So here we have now a graph, which is the torque against the speed for an induction motor when starting, right? And in this case, we are also considering the induction motor fed by a fixed voltage and a fixed frequency as well in the power supply. So the curve looks like this, right? So you pretty much, this is what your motor has available. But before we go any further, let me tell you guys what is my understanding on torque, right? For me, torque is simply energy, right? So this graph what you see here is the energy the motor has available to give, right? So that's what the motor has pretty much available to drive your application, right? And then when we talk about torque from your load, is what is the energy actually that your load is demanding from something. Because remember, the motor is driving an application, so it's giving power, or it's driving something, right? So I usually say the motor is the energy you have to give. Good. So let me get an example to you, because some of you may not understand why this is relevant, and I'll put in an example which I think it's easier for you to understand, right? So I'm getting another graph, and this time we'll get a torque curve, which is pretty much presented as a CR, which is a resistive torque, right? For a random application, okay? This is not specific to an application. I just got a random curve in there. Okay, so this is what my demand is, right? So let's assume we have a motor which has this torque curve, right? So the torque from your motor is what your motor has available to give, right? So when it's starting, you can see that the motor torque curve is higher than what your demand is, right? So because your motor torque is higher, then you can actually accelerate and spin this application, right? And then you can spin this application up to a point, which is this blue dot you can see in the graph, right? At that specific point, well, if you go any further than that, your resistive torque will be higher than that your motor has to give, right? So you won't accelerate any further than that, right? Good. So now let's change the motor. I'll get a smaller motor, and with this smaller motor, I get another torque curve for that as well, right? Let's assume first of all, let's assume that in this point, the blue dot, that's the rated speed. So we got the motor to accelerate to the rated speed, which is what we want, right? So now let's get to the second curve to a smaller motor, which is this curve in there, right? So what we can see, well, it is still fine, because when you're starting from, when you're getting the graph from this point up to the red dot, your motor torque is still higher than what your resistive torque is. So you're good to accelerate, right? But when you get to the red dot, it means that the motor won't accelerate any further than that. And why? Because your demand or your load torque is higher than what you have to give, or your motor torque. So you won't go any further than that, right? So it means you accelerate right to that dot, and then that speed can be slower than the rated speed for that motor, right? And we don't want that. When starting the motor, we would like to get the motor running at the rated speed, right? So in that specific case, this motor would be too small to the application, because the torque you're demanding needs to be, the torque you're giving needs to be higher than the torque you're demanding, right? Good. So now we understand the relevance of knowing the torque of the motors, and also in relation to your demand torque or your application torque. So let's move over, and I've got another graph to you just to summarize some of these things. So this is the motor torque, and this is the torque you have available, right, guys? So that's what the motor has available to give. So then we have the resistive torque in there. So we know this is demanded torque, or the torque your application is demanding at that time. And then we have this area here, which is the remaining torque. So this remaining torque, we call it as accelerating torque, right? So that's the energy your system or your motor have available then to accelerate that load. So the higher this area, or the higher your accelerating torque, the quicker you will get to the speed. Okay, so that's pretty much what I have in terms of the fundamentals of torque. And again, where can I find this information? Well, you can find this information in the motor curves, right? At least for WEG motors, we have this information available for majority of the motors we manufacture. So if you need a curve, let us know. We'll give it to you. And what you'll get will be something like this. So you have the red line, which is the motor torque. And then what we'll get as well is the green line in there, which is the motor current behavior when starting this specific motor, right? And then we'll get as well a few extra information in the bottom here, which is you may use as per your convenience. Okay. All right, let's move over. So what about my load or my resistive torque, my application torque? Well, I got a few graphs in there for some standard applications. For example, conveyor belts, your torque curve will look like something like this. And then you have for fans as well, we will look more parabolic. Also for your pumps, we will look more parabolic as well. And a way I have to think about it is like, for example, in a fan, as soon as you start accelerating the fan, the impellers itself will catch more air and put more air flow through, right? And that will increase the torque demand as well, right? But guys, this is information here regarding the application torque is then something you can get with the gear manufacturer. For example, the pump supplier or your fan supplier, they can get this information to you so you can size your starter properly, right? Good. I think we're good with the torque explanation. We know where to find the torque. We know what torque is, and we know why that's important to us. So what do we have to keep from this? Well, we need to understand then that the electric motor or the induction motor torque at a starting condition needs to be higher than the application load torque, right? So the machine can then accelerate and will accelerate to the rated speed. All right. So guys, I think we're done with the motor characteristics, right? And then I think it's time now to talk about the status, which is the intent of this presentation to you. Right, so let's move to DOL, direct online. Some other countries might be called it as direct online starter. All right, let's have a look how it looks like. Well, the DOL starter looks like this, right? It's a very lean and simple design. It's basically a switch contactor, right? And then you may have like an overload or fuses or protection as well to this device, but it's very lean. It's something like that. And to the power supply, we have L1, 2, and 3, which is it's the grid power line, right? So at that point, what you have is a fixed voltage and fixed frequency as well, right? So when you give the start command to the motor, what will happen is this. You will just close the main contactor, and that contactor will then feed your motor windings. So that's a straight start. So you go from 0 to rated voltage and rated frequency as well in one time, right? Very simple, very lean, right, guys? Okay, let's talk now about torque, right? So I got a load curve torque, which is random again, right? Any curve I put in there. And then I know that my motor behavior in terms of torque is something like this for the motor with the rated voltage and rated frequency, right? So when it's starting, I will get something like that, right? So we have available torque here up to this point where we have the rated speed, and then that's it. The motor will run at that point. Okay, so let's understand a little bit what this graph may bring us, right? So again, simplistic point of view, right? So this gray area is actually the energy your load is demanding, right, from the start. So this is what your demand is. What your motor has to give is the whole thing here, right? And then what you have in green is the accelerating torque, which we talked before, right? And that accelerating torque is actually the ability your motor has to accelerate, or the energy available your motor has to accelerate, right? So I think most of you might think, well, we are fine, right? Because the torque we have available is higher than what I need. Then I'm good. That will run beautiful, right? But, well, for this specific case, when you have a lot of energy available to start, that might be a problem to you, right? And why? Well, basically because when you have a lot of accelerating torque, that's a lot of energy you have to accelerate your application. Then what will happen? You will accelerate your application very quickly, right? So that will be abrupt. That will be aggressive as well. And in the mechanical point of view, when something is really aggressive, or you go from 0 to rated speed very quickly, it means you're putting a bit of a mechanical stress on your application, right? So I mean, stress might be like, for example, if you have a gearbox, your gears will go from 0 to rated speed very quickly, and then you might have like something like a kick when starting. And this kick or this abruptness or this aggressiveness, that might bring mechanical fatigue or wear to the mechanical parts of your application. So in this example that I've given is to the gearbox, you might have mechanical stress to the gears itself. On the other hand, let's say if we have a system with belts, you might start seeing a fatigue on the belts itself, or your belts may slip when starting, or you might start facing your belts snipping off as well, right? In couplings, you might have the fatigue on the pinions if it's a flexible coupling, or your machine, because you're doing this abrupt start, the ankle bolts might start getting loose. You might start facing misalignment, then vibration, right? So in the long term, when you're starting with a lot of energy available, this might bring you to issues that you need to get more maintenance to that system, right? Because you have to keep an eye open to that, just to be sure it's working as it should. So because of the aggressiveness, right? But that's it. We're going to talk about these methods. Some have more issues than others, but it's about you guys here to understand what the advantages are and take a decision for your application, right? Okay, so in terms of longevity, I think we touched base on what are the consequences for the GOL. So now let's change a little bit the perspective to the energy consumption or current, right? So for that, I'm gonna go back to the current graph, which is quite the same we've seen before in the motor characteristics, right? But it's something like that. Okay, so when we're starting then, we know that we have a current spike, and that spike can get 5 to 8 times what is the rated current of a specific motor, right? And that might be a problem in some of the sites. Imagine that you have on your site an application which is starting several times an hour, then that spike might be something, might be charged for you. So you will have to pay for that energy that you're consuming at that time, right? If you have like a very large motor starting and you're consuming this amount of current, you must start facing under voltage on your system as well, or on your site grid. And that could cause fluctuations in voltage on your site. And this is not good for the other equipment you have on site, right? So this spike is something we don't like. And well, because it causes energy consumption, okay? And you might get penalties or be extra charged for that. All right. So we know now in terms of torque or mechanically how the GOL starter works. We know now electrically as well how is the starting current for that specific method. So let me show you how this starter looks like, right? So the starter looks like this, right? Could be like a contactor plus an overload on it attached to the contactor, right? Or you may have something different, which is something like that, which is the a motor circuit breaker for protection, and also a contactor on it. Okay. In some of the cases, you might even have the circuit breaker plus an overload as well attached to that. And that's just to differentiate between short circuit and an overload, right? Guys, if this is your choice, WEG has a solution for you as well. We have a whole range of contactors and overloads to you. So if this is what you choose to put in your application, let us know. We have something to offer. Okay. So let's move over now to the next starter. I'll just get a bit of water, which is the star delta. Okay, star delta in some of the countries, it's known as well as Y delta, right? Which is another method. But before we touch base on the method itself, it's good to understand how we wire the motors, or what the induction motors connections are, right? So we can connect the motors in star. And guys, to be honest, I never saw a star from this connection. It's, for me, it's a Y connection, but a star, I could never see a star from that. And then we have a delta connection, which is something like this, right? You're connecting delta. So in the motor itself, you can arrange the winding, the phase windings in positions like Y or delta. Some of the motors we have the ability to do that. Some of the motors we don't, right? So in cases you have motors with only 3 terminals, probably this is wired inside, and then you don't have this ability to wire differently, right? Cool. So we know how the connection methods are. So now let's understand the principle, right? And the principle is very simple. So the principle of the Y delta starter is that you start in Y, and then at the end of the curve, when your demand for torque is higher, then you switch over to delta, right? And why starting in Y? Basically because at that method, we'll get less current on the, less voltage on the phase windings, right? So I got a graph in here with let's assume we have on site 220 volts on your line, or your voltage online. And the voltage on the winding itself of that specific phase will be 127 volts, right? And then for the same 220 volts power supply, what you get in delta is 220 volts, which means we are dropping by 58%. We're dropping to 58% of the voltage when using the Y connection, okay? So we have lower voltage, it means lower starting torque, it means lower starting current as well, which when you have a higher voltage means higher starting torque and higher starting current as well, okay? So we know the principle now. Let's have a look how it looks like. It looks like something like this, right? You have 3 different contactors. We have the power supply here on top, and this is already wired to your motor windings, okay? So when starting, I just moved K3 a little bit to the bottom here. But when we're starting in star or Y, that's how you're going to close the contactor K1 and contactor K3, right? And then you're going to get a star point in here. So this is clearly a star, right? And then you accelerate, you will have in the command a timer to say when it's time to switch from Y to delta. And when your time is gone, you switch it over then to delta, right? And then you will have something like that, right? You open K3 and close K2. Clearly a delta connection in there, right? So in general terms, or just for the power side, this is how it looks like. We have the command as well, which does have like the push buttons to start and stop, e-stop as well, resets, and the timer, which is important to this starting method. All right, let's go back to the torque graphs now. So let's assume again this load torque curve, and then we have something different now for the motor torque, right? So we have the motor torque, which is in Y connection, is the red one, or the star connections in red. And then in green, we have the same motor torque at delta connection, right? So when it's starting, we'll face something like this. It will start in star up to this point, and then your timer will click, and then you switch it over to delta, and then it will change to the next torque curve, which is the greenish one, okay? Cool. So let's have a look in deep on this the same way we did with the GOL starter, right? So what we have here is then slightly different. Do you remember in the GOL, we have all this area here in green, which was the accelerating torque, right? But for the star delta, we have something different. We have this bluish area, which is starting in star or Y. For me, it's a little bit hard to say starting in star. It's too much star. But yeah, so we have the bluish area here, which is when you're starting in Y. And then we have the switchover point, which is here when you switch it over from Y to delta. And then you have the delta operation, which is in red, right? So guys, did you notice here that we have a spike in the available torque or the acceleration torque on it? And when we have this spike, it means we are putting available a lot of energy to drive your application, right? So that spike might bring again what? The mechanical stress we face on the GOL, right? So mechanically speaking, this is a little bit better than what we have in the GOL, but because of the spike, is we still will face that abruptness or that aggressiveness when switching over now from Y to delta, right? Unless you get this point or this switch over point really close to the end of the starting period. Okay, so now we know regarding the torque on the Y delta starter. So let's move over now to the current, right? So to understand current, we need to understand how the current is in both methods. So here in the graph, I have the current in Y connection, and that's the torque. And then I have the current in delta connection with the torque curve as well, right? And I put a dot line here, that's the switch over time. So let's just visualize then the current. So this is the current in Y, this is the current in delta, right? So when you're starting, we're getting from here to the switchover point, and then your current will spike again, right? So talking about current consumption, this is a little bit better than the GOL, because in the GOL, we're starting from 6 times or 6 to 8 times the rated current. But for the Y delta, we can start with a lower value. But again, you have a bit of a kick or a bit of abrupt transition, which it could eventually not be healthy to your system or to your grid or to your installation, right? So again, we are seeing disturbance in there that we don't like, okay? Cool. So we are pretty much done with the torque and the current on the Y delta. Now, how does it look like? Well, it looks like this, right? We have now, instead of a one contactor, we have 3 different contactors and an overload as well. We manufacture and we can supply to you guys as well the bridges for that, right? So we have this configuration with the overload and this other configuration with the multi-circuit breaker on it. And if what you like, or if this is your choice of starter, we have the product to you as well, right? And by the way, there's a few extra things. This is only the power side, but we have the control or the command as well side with push buttons and the timer. And if what you're looking after is a complete solution, we do also have the enclosed starters, which is basically an enclosed box with all this gear inside, plus your command push buttons and timers on it as well. It's very easy to set. You can install it in your application and get your motor up and running in Y delta method. Okay, so guys, we are getting to the end of the star delta, and now it's time to talk a little bit now about the soft starter, right? Okay. So, well, basically the soft starter is a device that soft start your induction mode. Might sound really simplistic, but that's what it is, right? And how does it do that? Well, first and very important point here, the soft starter doesn't change anything on the frequency of your line. So the soft starter principle is just to play with the voltage level to your motor, right? And how does it do that? Well, I got a graph in here. So we have like the your power supply on top. And then here on the bottom, UVW, that's your phase, your motor phase connection, right? So we use semiconductors or SCRs on the soft starters to fire and chop the voltage to your motor. So what your motor is seeing as power supply will be a chopped version of the voltage you get in the supply, right? And that chopped voltage is effectively less than what you have on the mains, right? So you're getting effective less voltage to your motor. Beautiful. So the principle is quite simple to the Y delta, but the difference in here is that you can control this voltage all over the starting ramp, right? And the beautiful thing here we have is that today we have very advanced methods to control semiconductors. So we mastered the how to control that. So with that, we can pretty much adjust the voltage level as we want to the motor, right? So I'm gonna get an example to you quickly. So if this is the sine wave power supply here on the power supply, let's assume we have the SCRs firing this way, right? So the result you're gonna get on the output of the soft starter will be something like that. As I mentioned, a chopped version of the mains, right? And that effectively is something lesser than what you have in the mains. Beautiful. So that's the principle. Very simple thing, right? Okay. So now let me get you guys what are the options we have to start the motors with a soft starter, right? And for these examples, what I'll do, I'll use the methods we have available in our premium soft starter, which is the SSW 900, okay? So let's start with the ramps. Okay, I'm gonna start with the voltage ramp. So the voltage ramp is something like that, what you have in your graph. So you will set up what is your starting point in terms of voltage, and you set that up on the product HMI, which is here. So there's a parameter to set that. And then you also set what is your ramp time, right? So how long do you want this start to be? So what the starter will do, it will vary the voltage or the effective voltage to the motor in this way, right? Okay, Rafa. So where should I use these ramps, right? And the answer is quite simple. The ramps are usually used when you have applications where your starting torque is demand. Remember, we talked about the demand, right? So when the demand of your application in low speeds is lower, right? Or lower, lower. And then as soon as you accelerate, your demand starts to increase, right? So we pretty much do the same by varying the voltage as well. So you're giving less torque when starting in low speeds. And then as soon as you accelerate and increase the voltage ramp, you're giving more torque to the application. And if your demand is high as well, you pretty much follow what your demand is, right? Cool. So when you have light loads, and that's as soon as you start loading it up, like that graph as a pump, which is quadratic, that would be a very good option to use, okay? And guys, in terms of mechanical stress, usually the ramps are the best option for to mitigate that. So when you use ramps, and we'll see that later in the torque curves, that's where you have the best result, right? So the same as the voltage ramp, the soft starter brings as well a current ramp. So instead of varying the voltage, you can vary the current. And also there's something I like very much, which is the torque ramps as well. So you can set up your torque ramps to your motor via the soft starter, right? There's another method as well, guys, which is the limits, right? So we do have like this current limit, which means the starter will fire the SCRs to get to that current level, and it will stay in that current level until the end of the start, right? So we have that in current and in torque, right? And that's important for applications where current, mechanically, that's not the main reason why using the soft starter, but in installations where you have like current restrictions, right? For example, if you have an island with gensets and you can't go any further than a current level, that's where you use current limiting when starting, right? Okay, we also have some applications where we have friction, right? What is friction? Friction is when you have to, well, your application does carry, you need more energy to take it out from static position. And when it's up and running or start spinning, then your torque demand goes down, right? So you just need that kick just to take it out of the static position. So for that, we can use ramps like this, where we can set up the limits or the current limit higher, and then you go back to what your limit is. Or we can set up something which is like this as well, which is the same thing as the current, but now with torque. So we can set up different curves to the torque. Or we have something which is called kickstart, right? So the kickstart will be like, as the name says, a kickstart. It will give it a kick for a time that you put in this parameter there. So you can take it off from the from the static position, put in movement, and then you can go back to whenever method you're using. In this case here, a voltage ramp, or you could go back to a current limitation, or that, right? Cool. We've seen the methods now, a few methods to start the motors with the soft starter. Now let's go back to the torque, right? And to study that, I'll put the torque curves from the GOL and from the Y delta starter as well, just to make a comparison, right? Okay, so the voltage level, when we're starting with the GOL, it gets from 0 to 100%, right? When you're starting then with the Y delta starter, it gets then from 0 to 58%, which is the Y connection, and then keeps accelerating. And then when your timer is gone, bang, you have the delta connection again, full voltage, right? And we have the other method, which is now the soft starter with a voltage ramp, which we get to the minimum, to the voltage level we set as minimum, and then you have a ramp up to the maximum voltage level of that motor, right? So let's have a look on the torque-wise, how this looks like. Well, in the torque, we see here in red, that's the torque we've seen before with the delta connection. Then we have the bluish line, which is for the Y delta, right? So we have in Y, and then bang, you close the delta, here is your spike. And that's how it looks like when starting this motor with the voltage ramp. So it will be something with the greenish line in there. Clearly, you can see the mechanical stress is lesser than in the other methods, right? Okay, Rafa, what about the current? Well, the current will be something like that. So you have the red line in GOL, and then you have Y delta in blue, right? We have the spike. And then when starting with the voltage ramp, you have something close to the greenish line. So there's no abruptness on it. And also you fix your level. You don't have any spike on the current levels as well. Good, so now we understand how is the operation of the soft starter and what are a few of the benefits to you. So I would like to touch base on a few extra features the soft starter does carry. One is the internal bypass, right? So how does it work? Well, you need soft starter to start the motor, right? When the motor is up to speed, you don't need to, well, if you keep firing these semiconductors, you actually don't need that. So what do? We have a contactor to bypass. So you accelerate, when you get to the rated speed, you bypass, and then you don't need to use the semiconductors anymore, right? And that brings advantages, because when you're not using the semiconductors, it means your efficiency goes up. because we have more losses on the SCRs than what we have in a switch, which is the bypass contactor, right? And also in terms of reliability to the system itself, it's better to keep the bypass, because the bypass withstand to voltage fluctuations is better as well. Okay, so that's a very good feature we have on the SSW 900. Now, in terms of communication, there's a whole world of different things you can do with the soft starter. With the communication, you can pretty much plug this device to your system, and then you can watch live what the starter is doing. So you can get information like what is the motor power, what is the current consumption at that specific time. You can train if there's any fault, right, with the starter itself. You can train the starts. So there's an infinite options of different things you can gather from the communication of the starter itself, right? And also this, specifically for the SSW 900, you can also plug your computer when commissioning this unit to the starter, and then you can commission or get parameters from that using your computer, store the parameters on your computer so you can use in a later date. You can train the starts to understand how your work, how your current or how your torque is working at that specific start. So there's a few things you can do with this communication, right? And for the gigs, the SSW 900 also does carry a PLC internally, right? So what you can do, you can start decentralizing things and putting like small softwares on your starter. So you can sort of take keep one PLC on your GCS, for example, and then start getting different softwares elsewhere on your site, decentralizing things as well. Okay, it's a very good feature of the SSW 900. Okay, what else we have? We have the protections. I touched base before on the communication, but the starter does carry a few protections. For example, under and over current, under and over voltage as well. There's a list on it, and that's very convenient for you to assess faults and also to give more protection to your application, which means reliability, okay? So if you manage to see that from your SCADA system and you have the protections available, means your system is more reliable to faults. All right, so those were the features that I have to present. How does it look like now, Rafa, the starter? Well, it looks like this. We have different frames, right? So the smaller frames will be like this, and then we go up to 1400 amps on the larger frames, which will look more like this. All right. So guys, I think we're done now with the soft starter bit. So what I'll do, I'll just make a quick comparison between these starter methods, and that's pretty much for us to get that information stored in our brains, okay? So, okay, so let's first touch base on the power supply impact, which is energy savings, right? So for the GOL, then we know that your current consumption will be 5 to 8 times the motor rated current. With the Y delta, we know that we're gonna reduce this starting current by a lot, but at the end of that curve, you will have a spike again. So this is something not too good, but it's way better than what we have in the GOL, right? And then with the soft starter, we can adjust the voltage or the current to your start. So then we can manipulate how to use this and to get the best from your energy consumption on your site. Okay, so that's in the energy point of view. That's what we have. Now let's go to the mechanical stress perspective. So we have on the GOL the full torque available, full starting torque available, and then its accelerating torque is very high, abruptness, aggressiveness, and that's usually not good in the mechanical point of view because it brings stress, fatigue, wear, potentially vibration and failures, right? But eventually, if you have an application where you're not starting too many times an hour, or if you're starting one time a year, for example, maybe that's something you can deal with, right? And then we have the star delta, where we have the mechanical stress, only when switching from Y to delta or switching from star to delta. It's a bit better than the GOL with the star delta, because instead of getting that huge amount of accelerating torque available, you only have that when switching, right? And then we have the soft starter, which the mechanical stress is mitigated with several options to start your motor as your demand is or as you need. Okay, so let's touch base now with the additional features. Well, all the units here, you can implement overload protection, even to the GOL, star delta, and the soft start with the overload protection on it as well. The GOL has a great cost benefit. It's one contactor plus an overload, right? And a few other things if you like to make it more advanced. So it's the cost benefits really good on that. Now on the star delta, well, increases a little bit your cost, because instead of having one contactor, you have three now. And then you need command as well, you need the timer, right? So it's a little bit more advanced, but it's still fairly convenient price-wise. And then you have the soft starter, which does carry a lot of features, right? So you're getting a big improvement on the way you're operating your application itself, because it's visible to you on this SCADA system. You have communication, but that comes with a price as well, right? So in the price comparison, this would be the less cost-effective option. Okay, so guys, I think now you have enough to make a decision on which starter to use on your application, right? So you know the good points and the bad points on each method. So that's pretty much what I have to present to you guys today, okay? So I think we have a few minutes. I'll leave it open for a few minutes so you guys can get a few questions for our team to respond as well on this, right? And let me show you guys something. I'm gonna just touch base on our website, and for that I'll have to get this there. So okay, teams. So the website from WEG is the www.weg.net, right? So obviously, because I am in Brazil, I'm gonna get the Brazilian version, but here on your right corner top, you can change the language into English, right? And then you can get your country, all right? I'll get Australia here just because of my accent. If I can type it right. Okay, Australia, beautiful. So we are in the Australian version of the website. So if you guys would like to contact us, there's a way to do that with the website. So you can get to the support, and then you get to contact us. And then we will have a few options for you. So the first option will be contacting our branch in Australia. You have the address and you have the phone number as well on it, as well an email address if you would like to send an email to them. Or alternatively, the other option will be filling these fields in there, like the name, email, company, and so on and so forth, and leave a comment or a question for us in there and send, okay? So guys, we take very serious these claims from our website. So in cases need be, let us know. We would like to start building a relationship with you all, okay? Let me show you another feature from the website. I'm just gonna search for SSW900, for example, right? Which is our premium soft starter. And then if you get to downloads, you will have available there a bunch of documentation for the product itself, right? And then you can filter here by the type of a document you're looking after. Let's say, for example, I'm looking after a programming manual for the soft start. So I'll click a programming manual and I'll hit search, and then I have the document in there. If I click on it, it will open a PDF version of the document. You can save to your computer and use as per your convenience. So if you like to show your friend or someone at work how does this SSW900 works, you can get a product catalog from the website. If you're on site and you don't have phone reception, you can save this document to your computer and use as your convenience. Okay, so there's a few things that I strongly suggest you guys to have a look in the website. It's a very good tool we have to gather information. Right, let me close this one up, go back to my presentation. And how we are about time? Well, I'm spending a lot of, a little bit over an hour. Let me have a look in the questions. I'll respond one question just to, I don't want to take a lot of your time, but let me see one. Okay, I have a question here which is a bit opened. What it says, what about the motor maximum starting time? Okay, that's a very good question, but I guess the objective behind these questions is to understand the limitation of the induction motor when starting, right? And that's right. When you start a motor, well, we expect the current to be higher, right? And also what you have in the rotor bars of that motor is a higher current level as well. So the stator of the motor and the rotor of the motor will get with the temperature higher. Will eventually get hotter because of that inrush, right? And if you leave it in that inrush period for a long time, that might be a problem to the motor itself. You might run the motor in an over temperature condition, right? So to mitigate that, we have in the motor data sheet something which is called locked rotor time, right? So what is the locked rotor time? That's the maximum time permissible to your motor to start, right? So again, we are talking to here on making soft starts, or making smoother starts, which means likely longer starts as well. But those starts can't be any longer than what you have in the locked rotor time, right? So it's sort of you need to find the balance or the best point, right? You need to start long enough that you don't have the abruptness or the aggressiveness of a direct online start, but you can't go any further than the locked rotor time, because then you might start seeing consequences to the motor itself. Okay, so guys, I have an hour and 10 minutes quite. We have a survey that I would like you guys to respond, right? So get one of my colleagues to get the address or the link to this survey for you on the chat. And then I would appreciate if you guys can respond to that survey, right? That's important to us because it will help us to make or to get better events for you in the future. All right. So, okay, guys. So thank you very much for your time today. I hope you had a quality time with me, and you managed to learn something new with this session. This is the very last event from WEG Automation for the low voltage team to the market in 2020, this year. We are sort of getting to December. So for the guys that I won't talk again, I would like to wish you very good holiday seasons. Stay safe with your family during this hard time as well. And thank you and goodbye.